can move to the next speaker, which comes from the same group, Trinity College Dublin, Dr. Chris Kingsbury.
Hi.
Please, the rest is yours.
Sure. I'll just throw up my screen. All right. I hope you guys are able to see that. Go back to the start. That's working okay? Corollas, thumbs up?
Yeah, it's okay.
Cool. So I wanted to talk today for 20 minutes, half an hour, on the crystal engineering of the receptor porphyrins that we're using for chiral discrimination. This is a part of the project that relies strongly on crystal structures, and a lot of the work that I've been doing during the COVID shutdown has been on using crystal structures as big data and essentially trying to look at insights across many, many crystal structures that we can use for design principles and kind of hypothesis testing without having to go out and measure 9,000 crystal structures ourselves. So I think that Corollas has given everyone an idea of what a porphyrin is and how it is used in sensing. Generally considered, these materials are approximately planar, and with planarity comes a large degree of symmetry. The materials in their most general sense have this fourfold symmetric rotation, multiple mirror planes, and improper rotation axes. And that's true for most porphyrins, which have a relatively simple substitution pattern around the exterior of the ring. But porphyrins can be modified, and there are a number of techniques, a lot of them developed in our lab, for the generation of different types of porphyrins with different substitution patterns around the meso and beta positions and different identities in the inner core. And I suppose the important question that I'm trying to answer with all of this data is, can you design a particular shape of a porphyrin and a different particular chirality by modifying the meso and the beta positions in the inner core in order to get this structure-function relationship? Well, really, it's a shape, chemical structure to shape to function relationship. Generally speaking, the different approaches to chiral sensing are broadly to be put into two camps. So there's the lock and key principle, which is essentially that you have a predefined chiral cavity, which you can then place a molecule into. And that molecule, depending on the chirality, will either fit or not fit, and it will have a different interaction with some kind of sensor, be it electrochemical or spectrophotometric, that gives you a different signal, which you can use to discriminate the chirality of the guest. The second is chirality transfer, where the chirality of the guest molecule is imparted upon the host, and then the change in the host can itself be measured, where the change in the specific guest molecule can't necessarily. And this is what I'll be talking about for most of the rest of the talk, though both approaches are adopted by the initio groups. The main issue with using this approach with porphyrins is that it requires a specific spontaneous macrocycle chirality. You need to at least be able to have a chiral conformation of the host. Otherwise, the two signals, when you get the chiral discrimination, will be the same. And that's played out in the electronic states as well. So the A1U orbital is the, I suppose, highest occupied molecular orbital. And when you generate a chiral conformation, that A1U should become non-degenerate. And these orbitals are relatively consistent across all porphyrins. Talking about molecular shape, quickly wanted to talk about this man and his work, Professor John Shelmett. His work primarily in a lot of porphyrin-based nanostructures and coming from a physics background, using this normal coordinate structural decomposition method, which is a way of quantifying shape. So essentially, we're able to take a porphyrin molecule, a generic porphyrin molecule, and then decompose it into individual vectors, which allow us to understand the shape of the particular molecule. And it allows us to relate something like it is saddle-shaped to a specific number of how much saddle-shaped it is. And if we think of chirality in a near-symmetric molecule, which is what a porphyrin generally is, and I'll come back to that, the chirality that is engendered should be equivalent to some chiralness parameter. And I believe that a normal coordinate method is a great way of determining at least something which is correlated with that chiralness parameter. So when we talk about normal coordinates, what are we talking about? It's a kind of coordinate transform and very simple to understand. So instead of discussing molecules as individual points in space in Cartesian coordinates over on the left, each individual atom could be talked about in terms of a distance or talked about in terms of polar coordinates. And this is really no different from that. This coordinate transform, instead of looking at things in Cartesian coordinates or in the X-ray space coordinate frame, you instead can look at these things in terms of pre-computed normal coordinates, which are like vector fields, and how well each individual molecule fits into these predefined vector fields. And over on the right is kind of a simplified example that we can take a molecule, decompose it into these, and then look only at the symmetric representations that we're interested in, which are the ones which are able to break symmetry and are above a certain threshold that we know that they're going to be present both in solution and in the crystal structure. A general note on how porphyrins distort. There's a number of methods, but these are probably the most common, and each has a particular symmetry representation. I'll refer to these a touch through the rest of the thing, but it's not important to keep them in mind. Generally, that the out-of-plane distortions are a little more easily accessed than the in-plane distortions. So when we're quantifying porphyrin distortion, generally how it works is that you take the experimental positions, we use a linear algebra, least squares, to relate those to our pre-computed normal coordinate matrices. And what we get out is a set of vectors, essentially transforming this into our normal coordinate space. And that is a method that can go both ways. So once we have a material which has a certain set of vectors, we can compute back the Cartesian coordinates from those vectors. So it's bidirectional in terms of being able to both measure and also generate molecules. And this methodology is very essentially static across many different measurements. We can see here, this is the photobiology of a few different active sites within 2 different species. And we can see that the error bars, you may not be able to see them, very small. It means we're having a very consistent shape between different measurements of essentially the same molecules in slightly different coordination environments. And this has a strong determinant on the photochemical structure of these porphyrinoid molecules. Now there's a touch of a hitch. The original NSD program was designed for working on 1 molecule, and most of the original tools were lost when Sandia National Labs took the NSD server offline. And unfortunately, the surviving method is, I'm going to say, a little clunky. And there's the potential for future compatibility issues. So essentially trying to redo this method and re-engineer it so that we can allow for database parsing. We can look at the investigation of different data structures and potentially try and do some of this automatically. So I've remade the original program. Generally works by using these open source technologies. So that ensures compatibility with the future, and it ensures that anyone can read and understand what's written. Generally, we're getting an output which relates that structure to the normal coordinate frame, and should be relatively simple to understand and able to be added on to any document as supplementary information. Additionally, there's tests that are performed, and this is based on some of the structure cluster fitting that we've been doing on different parts of the molecule, different parts of the NSD representation. When we're talking about molecular structure as big data, we're talking generally about the chemical structure and shape being more or less equivalent. We're saying the first part of that is that the chemical structure is a determinant of its molecular shape and how closely these 2 concepts are related. I'll come back to that in a little bit, but it's probably more directional than you may think. That generally, when we're talking about a molecule, by knowing its structure, we can have a general idea of, by knowing what the identity is, we can have a fairly good guess of what the structure is going to be. And also, this is generally a methodology which uses some of the data that people often throw out when they are looking at crystal structures. So crystal structures are usually used simply for molecular conformation. Anyway, this is the first plot, and you can see that each circle in here, I suppose you can't see it, that each circle represents an individual crystal structure. And these are the crystal structures of the saddle-shaped porphyrins, which I'll show again on the next slide. A specific kind of bend, which is a result of molecular crowding around the external periphery of the porphyrin. And you can see that very strongly in this, that as you go to the right-hand side with the more distorted porphyrins, you also get a reduction in a number of hydrogen atoms, presumably the least involved, the least sterically demanding of the periphery substituents to get, as those numbers are reduced, the porphyrin becomes far more distorted. And if you know something about the chemical structure, you can have a fairly good guess that your porphyrin, a novel porphyrin, would exist somewhere within that dark cloud. It's a little more involved plot, and I've highlighted a few clusters here. So the open circles are the dodecaporphyrins. The closed green circles, the porphyrin diacids, and the yellow circles, the multiply alkylated porphyrins with alkyl groups at the core. What we can see from this quite clearly, I should hope, is that these are the porphyrins that we should be focusing on, because these are the ones which are most adept at being able to accentuate, to show this strong non-planarity. And as we said before, this non-planarity is what breaks the symmetry and allows us to then take the broken symmetry molecule and relate that post chirality to the chirality of our guest molecule. Not just out of plane though, there are also some modeling of the in-plane structure of that. And we can see that each of these forms a relatively tight cluster and tight and isolated cluster. So these are the 515 substituted porphyrins, essentially substituted at those differential carbon meso positions. That when we look at different substitution patterns, we can see quite strongly that the atom positions are relatively well known. That these clusters have approximately Gaussian shape and can be fitted with a relatively normal Pearson's tri-squared relationship. From this clustering behavior, we can now treat new porphyrin structures not as necessarily a point on this graph, but as another data point which can be related to a whole group. If we're thinking about this, it's possible that there's a general insight onto molecular shape. So porphyrins are relatively complex molecules with a lot of different methodologies by which they distort. But at most, they can be modeled usually with 4 to 5 parameters instead of the full 72 that we would need for a full least squares refinement. 96% of each individual molecule's distortion can be summed up by using its minimum coordinate frame, just the principal components of the distortion vectors. And knowing this, we can kind of understand that it's possible that by using this kind of symmetry-based reduction, we can actually get a better model, and then we can use that model to feed back into structure determination, potentially having a use for lower data structure determination methods. Unfortunately, this is not the most approachable of data reporting formats. I understand it, but I've spent a good year understanding it. It's quite hostile. So the process, I suppose, next is to try and get a way of making this a little more open to the people that may want to use a method or a similar method. And I wanted to talk a little bit about this man, Pierre Mondrian, and his work on non-representational art, essentially saying that art and reality should themselves stand at antipodes. And this is somewhat what we're trying to represent, the actual molecular structure of a material, the individual positions of atoms measured by crystal structures is very, very fine in terms of being able to determine atom positions very, very accurately, but not necessarily that informative. So we need some way of plotting those different distortional modes in order to understand possibly what the compromise is between the very, very fine molecular structure and the very coarse approximation that we would get from the assumption that it was a general porphyrinoid. Essentially, that there's got to be some compromise here which relates to the in solution structure. And if we can find a way of demonstrating that so it comes out bright as day. We've borrowed a little from Pierre Mondrian and generated this Mondrian type plot of the molecular porphyrinoid symmetry. You can see here a 515 disubstituted molecule. That 515 has a representation B2G. And we can see on the right-hand side in the Mondrian plot, the upper right corner is somewhat representational of the idealized structure in D4H, and the lower left, the measured molecular structure in CI. The closer these representations are to the upper right corner, the more likely they are to persist into the solution structure. You can see the most dominant and at a value of close to 1 is the B2G representation, and that is that 515 stretch we were talking about, resulting in a symmetry of D2H. These get a little more complex as you involve non-planarity, and we can see between these two structures, the in-plane structure is relatively similar, quite easily just by looking at the plot, whereas the out-of-plane structure in this EGX plus Y mode shows a strong distortion that relates the symmetry to C2H. And this more or less can be just simply read off the graph. Each of these structures has an inversion center and therefore probably not going to be useful for chiral sensing. But if we look at something that is related with the diphenyl saddle shape, we can see quite clearly that the Mondrian diagram in the middle right hand quadrant shows a representation in D2, which is itself a chiral group, and I've marked that with an asterisk. Similarly, this is one of Corolla's structures with the benzene sulfonic acid, and we can see that that has its own representation in C2, which is formed on the coordination of the acid. And we can see that that is generally because of that different interaction with the two sides of the porphyrinoid molecule. That molecule, that Y shape that Carolus was talking about, is actually necessary for the molecule to be able to adopt a chiral shape. This kind of structural analysis in a really important way allows us to look at what the components of our crystal structure are actually telling us about the symmetry and which are the important components and how to engender them in the materials that we're generating. Finally, I'll just, only a few slides left on Pierre Mondrian himself. I found this kind of cute periodic table, which is in the style of Pierre Mondrian. And this was for the 100th year of the periodic table, I believe. The style, the representation of chemical ideas using those simple blocks of color, I think is a very powerful thing. My own periodic table, the periodic table of porphyrin distortions, is generated from those NSD parameters we were talking about there. And we can relate how a porphyrin interacts with the core of, a individual atom interacts with the core of a porphyrin and the effect that that has on the individual shape. And this was presented as part of the International Year of the Periodic Table last year. So moving on, the general idea of the NSD method is that it relies on these pre-computed normal coordinate modes, which is good if you've got them, as we do for porphyrins, but wondering whether it's possible to bypass these NSD vectors. And we've developed a new method called SCSD, which essentially allows us to get that same information without having to do any pre-computation. And it's very exciting. We're looking at how much this can be used for different avenues, specifically in material science and in photomedicine. But hopefully this should be an easy to understand general method of essentially marrying structural chemistry with data pre-computation and data reduction for machine learning. Finally, I suppose what we're looking at is being able to generate an array of porphyrins. And this is a very nice example of a detector array used for looking at different solvents and different small molecules by Ken Susslich, where using different core atoms with just TPP allows us to get a very clear idea of what an individual molecule's identity is. And perhaps we can do the same thing with different molecules with different shapes. Generally, NSD and what we've been talking about allows us to quantify the chirality, display that information, and to use the insights for design. I think I should have put in a fairly strong basis for the diacid free base porphyrins with a 515 and beta substitution being likely the most chiral of these receptor molecules we can hope for. Just remains for me to thank the group at Trinity College and Matthias Senge, and for the funding agencies for giving me this opportunity. Thanks very much.
Sorry, Chris, if you go in the chat, you can see the, sorry for the microphone off.
That's okay. How do I get into the chat?
Okay, I can read the question. Thanks, is from Victor Brovko.
Yes.
Thanks for the interesting talk. Indeed, this is a nice approach. However, how can you relate it to chirality in a porphyrin molecule? Are there any structural direct parameters related to the chiral non-racemic deformations?
So, I haven't frozen, have I? You can hear me okay?
Yeah.
Generally, what the two different parameters are the ones which I believe are going to be the best chance. We've put together a review on this, but the best idea, I suppose, is going to be that multiplication of the two B2U and B2G parameters to generate a totally an asymmetric version. In terms of sorry, I will try and get that up. Oh, sorry. In terms of making one overarching parameter, we found that the A1U distortion is really not that present. that most of the time that could be related to noise. So that would be our one chance at generating a single overarching parameter, but unfortunately that isn't the case. Hope that answers your question.
Okay. Are there more questions? No?